real gas behavior and equations of state. In section 3.6 and 3.7, we examine PVT behavior of gases and we define the compressibility factor. Compressibility factor we then proceeded to develop the generalized compressibility chart. Figure D1. Generalized compressibility chart. Presented in appendix figure D1 in terms of reduced pressure and temperature. Reduced pressure and temperature. PR and TR. The generalized chart does not apply specifically to any one substance, but is instead an approximate relation that is not applied specifically to any one substance, but is instead an approximate relation that is reasonably accurate for many substances, especially those that are fairly simple in molecular structure. In this sense, the generalized compressibility chart can be viewed as one aspect of generalized behavior of substances, and also as a graphical form of equation of state representing real behavior of gases and liquids over a broad range of variables. In this sense, the generalized compressibility chart can be viewed as one aspect of generalized behavior of substances, and also a graphical form of equation of state representing real behavior of gases and liquid over a broad range of variables. Generalized charts. Graphical form of equation of state. Representing real behavior of gases and liquids over a broad range of variables. They gain additional insight into the behavior of gases as low density. Let us examine the low pressure portion of generalized compressibility chart in greater detail. This behavior is shown in this picture. The isotherms are essentially straight lines in this region, as shown in this picture. TR, reduced temperature, 5, 10. Note that the slope increases as TR increases. slope increase as TR increases. Note that also until a maximum is reached at TR about 5, until 5, and after that a slope decreases toward the Z equals 1 line for higher temperature. At single temperature about 2.5 times the critical temperature for which limitation is defined as the boiling temperature. Of substances. A single temperature about 2.5 times TR. This is only the temperature at which a gas behaves exactly as an ideal gas at low but finite pressure, since all other isotherms go to zero pressure, as shown in the picture. To simplify this bond, let us consider the residual volume alpha. Consider the picture again. Alpha equals to RT on P minus V, residual volume. Multiplying this equation by P, RT minus PV. Thus, the quantity alpha P is the difference between alpha P is the difference between RT and PV. RT from ideal gas and real PV. Now we can calculate that when P goes to 0, however, it does not necessarily follow that alpha Instead, it is only required that alpha remains finite. The derivative in this equation limit P from which we find that alpha tends to 0 as P goes to 0 only at boiling temperature. So let me write the relation again. Alpha P PV from this picture, or PV goes to RT at P tends to 0 alpha 0. Since that this is the only temperature for which the isothermal slope is 0. Isothermal slope of 0 in general. However, the quantity RT on PV does not go to 0, but is instead of small differences between two large values. This does have an effect on certain other properties of the gas. The compressibility behavior of low-density gases, as noted in the figure above, is the result of intermolecular interaction and can be expressed in terms of equation of states called the virial equation. Compressive behavior of low density gases. Behavior of low density gases. Which is derived from statistical thermodynamics. Z equals to PV on RT CT DT where BT, CT, DT are temperature dependent and are called the virial coefficients. Equation virial equations and BT virial coefficients. BT, CT and DT temperature dependent are called virial coefficients. BT is termed the second virial coefficient. And is due to binary interactions on the molecular level. The general temperature dependence of the second virial coefficient is as shown for nitrogen. If we multiply the general temperature dependence of the second virial coefficient is shown for BT in this picture. If we multiply the virial equation by RT on P, we can obtain this relation RT on P minus P on PV second. In the limitation, when P goes to 0, and we conclude from the previous relation, say that and also and the limitation equals to the single temperature at which Vg equals to 0. Figure show the single temperature, this point, is the boiler temperature. The second viral coefficient can be viewed as the first order correction for non-ideality of the gas and consequently becomes of considerable importance and interest. In fact, the low density behavior of the isotherms shown in the figure before this figure is directly attributed to second viral coefficients. Another aspect of generalized behavioral gas is the behavior of isotherm in term vicinity of the critical point. The generalized behavior of the behavior of isotherm shown in the vicinity of critical point. If we plot experimental data on PV coordinates, it found that the critical isotherm is unique in that it goes through a horizontal inflection point at the critical point, as shown in this picture. The plot of isotherm in region of the critical point on pressure volume mathematically, this means that the first two derivatives are 0 at the critical point, this point. PC, where the at critical point round P and around V2 critical point, a feature that is used to constrain many equations of state. To this point, we have discussed the generalized compressibility chart, a graphical form of equation of state Imperial equation, a theoretically founded equation, is a generalized behavior in form of empirical equations relying on a specific PVT data on their constants. The oldest generalized equations, the van der Waals equation, oldest generalized equation, van der Waals equation, is a member of the class of equation state known as cubic equation. Presented in Chapter 3 as figure equation 39. This equation was introduced in 80 equation introduced (1873) as a semi-theoretical improvement over the ideal gas model. The van der Waals equation of a state has two constants and is written as P V minus B. The constant B is intended to correct the volume occupied by the molecule. B correct the volume of the correct the volume occupied by molecule and the term A on B2 is a correction that accounts for intermolecular forces. Forces of attraction. In particular, these constants are evaluated by noting that the critical isotherm passes through a point of inflection at the critical point and that the slope is zero at this point. Therefore, we take the first two derivatives with respect to V of equation and set them equals to 0. According to the equations for critical points, which was introduced here, then this pair of equations along with the equation of van der Waals, these two equations, we have rho P or rho V at critical point RT and rho 2 at critical point. We see applying to Van der Waals equation, which is P we have this equation Vc equal to 3b, A equals to RTC the compressibility factor at the critical point for the Van der Waals equation is therefore ZC PCVC RT 3 on X for the Van der Waals equation, and which is considerably higher than equal actual value for any substance. Another cubic equation of a state that is considerably more accurate than the Van der Waals equation is that proposed by Redlich and Wundt equation. P equals to RT on V minus E with A equals to R2TC and B equals to the numerical values in the constants have been determined by a procedure similar to that followed in the Van der Waals equations. Because of its simplicity, this equation was not sufficiently accurate to be used in the calculation of precision tables of thermodynamics properties. It has, however, been used frequently for mixture calculation and phase equilibrium correlation with reasonably good success. Several modified versions of this equation have also been utilized in recent years, two of which are given in Appendix B. Empirical equations of states have been presented and used to represent real substance behavior for many years. The Bit-Brinkmann equation contained 5 empirical we provide another equation of state, the Bit-Brinkmann equation Bridgman. Equation contains 5 experimental constants. Was introduced in 28, and in another equations, the Benedict-Webb-Robin equation, Benedict-Webb-Robin equation, commonly termed the BWR equation. Equations extended that equation with 3 additional terms in order to better represent higher density behavior. Several modifications of these equations have used over years and often correlate gas mixture behavior. One particular interesting modification of BWR equation is the Lee-Kessler equation. One particular interesting modification of BWR equation of BWR equation of states is Lee-Kessler equation. Which was proposed in 1975. The equation has 12 constants and is written in terms of generalized properties as Z PR V prime R on TR equation. The one particularly interesting modification of BWR Lee-Kessler equation. C V prime 2R from G V prime 5R C4 TR3 V prime 2R beta plus gamma V prime 2R multiply to exponential minus gamma on V prime 2R, where V C T R B1 TR B3 on Tr2 minus B4 Tr3 and C1 minus C2 Tr3 and D equals to D1 plus D2 on Tr, in which the V prime R is not the true reducing specific volume but is defined as V prime RTC on PC. Empirical constants for simple fluid for this equation are given in appendix table D21. When using computer software to calculate the compressible factor Z at a given reduced temperature and reduced pressure, a third parameter omega, the centric factor defined and values listed in appendix D, can be included in order to improve the accuracy of the correlation, especially near or at saturation state. In the software, the value calculated for the simple fluid is called Z0, while a correction term called the Z1 is determined after a different set of constants for the Lee-Kessler equation of state. The overall compressibility Z is for software Z omega Z1. Finally, it should be noted that both the equation of state use a different approach to the representativity behavior in calculating the thermodynamic properties and tables. This subject will be discussed in detail in section 4011. The next section is about the generalized charge for change of enthalpy at constant temperature.